learn how communication satellites stay up there in one spot, like. And we went to a place that had all sorts of wire and no cheese. But first, here's how an internal combustion engine works. Why don't you people write in and ask for items about cheese?
In the 18th century, mankind developed a way to put burning fuel to work. It was used to turn water into steam. The expanding steam was used to push a piston, and the piston turned a crank. The shaft with the crank moved trains and boats, did farm work, and changed society completely. Steam engines were heavy and huge and needed a constant source of water. The piston and the crank themselves could be light and portable, but the external boiler and the fire were none too portable. Burning fuel to do work was a good idea, if only we could make the combustion take place internally. In this small internal combustion engine, there's a piston that can slide up and down in a cylinder. The piston is connected to a crank so that as the piston moves up and down, the crank can turn the shaft. At the end of the shaft on my end is a flywheel, just a heavy wheel. Connected to the crankshaft is another shaft with bumps on it. The shaft with bumps on it turns at half the speed of the crankshaft. As that camshaft turns, the bumps are made to open a couple of valves at the top of the cylinder. The one at the back opens a passageway to the carburetor. The carburetor has a small nozzle and a pool of fuel, and as air rushes across the top of it, it sucks a small amount of vaporized fuel with it. So, how does all this stuff do work? Well, as the piston moves down the cylinder, it creates a vacuum. One of the bumps on the camshaft is moved to push that back valve open, so air mixed with fuel rushes into the chamber. When the piston gets to the bottom, it starts back up because it's on the crank. But by now, the bumpy shaft has let the valve close, so the air and fuel mixture is just being squoze. At the top, a small spark from the spark plug ignites the air-fuel mixture. The reaction creates expanding gases that force the piston back down, adding power to the rotation of the crankshaft. Now, remember the flywheel at my end? It's heavy enough to keep the shaft turning, so the piston starts its travel back upwards again. Only by this time, the bumpy shaft has pushed the other valve open, so the exhausted gases get forced out here. The periodic explosions are enough to keep this whole thing spinning on its own. This is a general purpose engine. It's found in water pumps and generators. It's called a 4-cycle engine because there are 4 distinct operations. Sucking in the gas and air mixture, compressing that mixture, going bang, and exhausting the burned gases. The power that the engine gives is directly related to the amount of fuel that explodes in that chamber. There's a small valve on the carburetor that controls the amount of fuel by controlling how much air the engine can suck. The speed of the engine is controlled by the exact timing of the spark that ignites the mixture. And the throttle control usually operates the carburetor valve and the timing together. A car engine is a lot like this one, except that it has multiple pistons that share a common crank. These things are the famous piston rings. They're made from springy metal and expand outwards to form a good seal between the piston and the walls of the cylinder. The bottom ring prevents oil from creeping up into the combustion chamber. Oil? Well, you betcha there's oil down here. Best way to describe how these parts fit is perfectly. Without being well lubricated, an engine will just turn itself into scrap rapidly. This engine uses a splash method to oil all the parts. The bottom's full of oil, and a finger on the crank throws it around. Some engines, like the one in a car, use a pump to distribute the oil. There's a way to get rid of a lot of these parts. No. The 2-cycle engine. The 2-cycle has no valves, no camshaft, no oiling system. Instead, it has a bunch of carefully located holes and passageways. The carburetor is mounted down here in the base of the engine, in the crank casing. In front of the carburetor are some one-way reed valves. They work like this. Now, whereas the 4-cycle engine does 4 different things one at a time, the 2-cycle engine does 4 different things 2 at a time. Imagine that the piston's on its way up, compressing the gas mixture. The bottom of the piston is creating suction that draws in more air-gas mixture below it. When the piston reaches the top of its travel, the spark plug ignites the mixture and drives the piston back down. But the new air-gas mixture below can't go back through the one-way reed valves. Instead, it gets pushed up through a passageway right about here, if the engine weren't cut away, to the top of the piston, where it pushes the exhaust gases out of another passageway. The top of the two-cycle piston is shaped to direct traffic between incoming mixture and outgoing exhaust. On the next stroke, the entire operation repeats. The two-cycle engine has a further bonus. Since the air-gas mixture travels around all of the moving parts, oil can be mixed with the fuel to lubricate the engine. Now, outboard motor owners, stay seated. Everybody else, go grab a sandwich. It'd be a shame to give this cutaway back without looking at some of the things that are unique to outboards. Outboards are just about all water-cooled. Something to do with the abundance of water in their operating environment. The water pump is down here in the lake. This finned wheel is in an egg-shaped container that causes the fins to create little chambers that squeeze and unsqueeze, driving lake water up to the engine through this tube. Ah, look down here. This is your go-maker, forwards and backwards. Aren't you glad you stayed? A little knowledge is always better than a sandwich.
Banana. I should get out of this business.
What do you suppose the most abundant thing on Earth is? Acme votes for wire. Wire as we know and love it comes from the Earth, but we're going to pick up the story here, after it's been mined, smelted, and rolled into rods, 5/16 of an inch in diameter. Drawing wire is simple in concept. Pull the rod through a small hole in a die. But the details are interesting. To reduce the rod to a much smaller size requires several reduction steps. At any instant, the machine will have many dies, each with a bigger diameter entering and a smaller diameter exiting. So, how the heck do you thread the machine? The dies are all threaded externally. A machine called a pointer, sort of like a big pencil sharpener, chews a piece of wire down to size that will thread the first die. Then a length of wire is drawn through it. Successive dies are threaded the same way. Once a long section is prepared like this, it can be installed in the machine. The machine is filled with lubricant while it's running, so it has to have its covers closed. Here's another drawing machine ready to roll. Large capstans pull the wire along through the various dies. Their large size gives lots of surface area to develop enough friction to pull the slippery wire along. The motor that runs this machine is a 250 horsepower electric job. Rod enters the machine fairly slowly, and it exits fairly rapidly. The speed difference is due to the relative diameters of the input and output. In other words, a little bit of fat wire makes a lot of skinny wire. Each successive capstan in the machine has to turn at a slightly faster speed as the diameter decreases. This machine is spewing wire at a rate of 3,500 feet per minute. Outcoming wire is annealed and steam cleaned. Annealing is done by passing the wire over electrically charged rollers that cause the wire to heat up. The hot wire is then cooled in a bath. Annealing makes the wire soft and flexible. If you want to study the need for annealing, try to bend and then unbend a paperclip. Drawing wire is a continuous process, and continuously capturing the drawn wire is done by this machine. An empty spool is always on standby. When the first spool fills, the machine transfers the wire to the empty one. A gizmo called a dancer takes up any slack during the transfer. Here, individual wires are formed into stranded cables. These particular cables are being double-stranded for strength and flexibility. Large cables like this are used by utility companies. This production line is insulating a stranded cable by extrusion. Essentially, the wires enter a hot unit that's supplied with melted polyvinyl chloride plastic, PVC. As the wire leaves a nozzle, the PVC comes along with it. The hot plastic is still molten as it leaves the nozzle, so it goes through a long cooling trough filled with water. This little wheel is printing the manufacturer's name and the gauge and type of wire on the underside. All insulated wire goes through a unit like this. It's a sparker. High voltage is applied to these chains, and any arcing through the insulation will set an alarm. PVC for the extrusion machines comes from big boxes of PVC beads. The machine has a reservoir of melted plastic in it, and periodically a load of beads is sucked out of the box as the plastic is used up. Any guesses as to what's being made here? A black, white, and bare copper wire in a white jacket. This is good old 14-2 house wire. I found out the difference between the NMD and NMW versions of this stuff. NMD, non-metallic dry, and NMW, non-metallic wet. The wet version has a fungicide and it's more impervious to moisture, but it doesn't have the same resistance to heat as the dry type. Non-metallic wet shouldn't be used inside walls. They make about 1.5 million meters of this wire a month. This machine is a bow twister. One place that the output of the bow twister goes is the place I've always wondered about, the armored cable machine. The twisted, insulated wires are first wrapped with paper and string. Then a metal band is formed into the armor. This all happens pretty fast, and fortunately we had the magic Acme high-speed freeze-frame camera with us. Well, actually this is just another machine that happened to be stopped at the time, but you can see the spiral die that winds the armor. If the form of the final package allows, the wire's tested for continuity and sparked for insulation integrity again. These are the packages that you and I are most likely to buy. Utility companies get their large cables on huge spools that have been tested by immersion in water while connected to thousands of volts. At the moment, water is the most abundant thing on Earth. Considering this visit to just one of this company's plants, wire may be running a close second. Noticed that our brains have a kind of a curious cutoff point when it comes to technology? If I told you I was going to drop a brick on your foot, it would get your attention. If I told you that I was going to put a couple of tons of metal in space, 23,500 miles above the equator, and that would stay in one apparent spot as the Earth rotated and hurled through space, and that the 47,000-mile round trip would make the reception of TV signals and phone calls more efficient, what would you say? That's nice. Communication satellites raise some interesting questions. How do the satellites stay in one spot? How do the signals travel 47,000 miles when I can't get channel 3 from 100 miles away? Given the quality of what we see on TV, is this all worth it? Well, in the spirit of not biting the hand that feeds one, I'll let you decide the answer to the last question. When you throw something straight in the air, it defies gravity for a while because of centrifugal force. If nothing else affected the thrown object, it would just go hurtling into space in a straight line. The two other forces that do act on a thrown object are gravity, that pulls its path into a curve, and friction with the air, which slows it down. As the object slows down, gravity overcomes centrifugal force and the object falls to Earth. In space, there is no air friction, and a thrown object only has centrifugal force sending it outward and gravity pulling it into a curve around the Earth. An object thrown in space will circle the Earth forever if nothing else interferes with it. To get an object to orbit the Earth, the two forces have to be equal. If the object's moving too fast, it goes further out into space. If it goes too slow, it falls in a big spiral towards the Earth. Now, since the effect of the Earth's gravity diminishes with distance, the speed of the orbit is tied to the object's distance from the Earth. An object orbiting close to the Earth will circle it several times a day. The Moon circles at over 200,000 miles. It takes about 28 days to make an orbit. An object 23,500 miles above will have to circle the Earth once a day. Now, since the Earth also spins on its axis once a day, if an object's set to orbit 23,500 miles above the equator in the same direction as the Earth's spin, it'll appear to stay in one spot over the Earth. That's how. Now, why? There are three main ways to send communication signals. They become 4 ways in combination and 5 ways by interpretation. One way is to feed them down wires, 1 signal per wire. There are millions of single signal wires crisscrossing the continents. This method's called baseband. Another way is the modulation of high-frequency electromagnetic waves. The waves travel in all directions and can be picked out of the air by an antenna. It's called broadcasting. The third way is to put a lot of those modulated electromagnetic waves down a piece of wire on different frequencies. Best name I can come up with is wired frequency domain multiplexing. You can call it cable TV. The fourth way may eventually kill all the other ways, fiber optic transmission. Fiber optic communications uses incredibly high-frequency electromagnetic waves called light. This particular technology can cram a lot of stuff into a tiny, cheap fiber. The fifth method is like the second and fourth methods, microwave transmission. Microwaves are electromagnetic waves, like broadcasting, but at the wavelengths involved, they act like light. This allows the transmission to be focused in a beam. All microwave transmission uses parabolic reflectors, like the one found in a flashlight. Now, I got a little demo here, but it requires us to turn the iris down on the camera. See, for microwave dishes to work well, they need to be pointed at each other. On Earth, This works over as long a distance as you can muster until the curvature of the Earth blocks the beam. With one of these terrestrial links, it's very difficult for more than one dish to receive the transmission. Things change if one of the dishes is 23,500 miles in space. Dishes all over the continent could see it. That's all a communication satellite is, a big dish in the sky. The actual antennas are very small, just a few inches, and the dish only collects and focuses the wave onto the antennas. This is master control at TV Ontario. TV Ontario's programs are fed to a lot of transmitters scattered over the province of Ontario. Satellites turn out to be the most efficient way for one point to feed many. These two monitors quietly tell the satellite story. The trip up to the satellite takes about 1/8 of a second at the speed of light, and the return trip takes another 1/8 of a second. Yes, folks, Toronto sees the programs 1/4 of a second earlier than the rest of the province. Write in and complain. The transmitters on satellites are very low power compared to a broadcast transmitter. Part of the reasons the signals can travel so well has to do with the fact that they're focused into beams. But the rest of the reason is that they only travel through a few miles of atmosphere. There's very little loss out in space. The universe isn't perfect. To keep a satellite sitting over one spot on Earth takes constant fiddling. The adjustments are done with high-tech aerosol cans. The satellite comes to the end of its life when it runs out of spritz. I think I know the feeling. Next week on Acme, I don't know. See, this is show 13 of a 13-part series. So if you do see me next week, it's either show number 1 repeated, or I'll be a year older and I'll be wearing a brand new shirt. I can hardly wait for next week.